Yeah, so I decided to shorten the title a little bit, just so it could fit in, because these giants are really big. So traditionally, M giants, or pulsations and variability of these stars, have been analyzed using this diagram here called the period luminosity diagram, where one plots the logarithm of the period on one axis and the luminosity, or some proxy of it, on the other axis. And for a long time, we have known that those periods fall on certain ridges in this diagram. And most of these ridges are thought to arise from pulsations, fundamental and overtone modes. But all along, there has been quite discussion on the actual radial order of each of these ridges. To aid that analysis, another diagram has been used called the Peterson diagram, where on the y-axis we now have period ratios. So you essentially take any two pair of periods and take the ratio and plot that for a number of stars, and you get a diagram like that, which shows a number of features and some fine structures that people have tried to explain. It has been a quite vigorous field in the last 15 to 20 years. Here's just a snapshot of some of the main papers that have been going on for that period of time. They have in common, many of them have tried to explain the ridges, the structures that were believed to be modes, as being purely radial modes, with some limited success. And so over the last 5 to 10 years, there's been increasing support and evidence for that non-radial modes play a role. So a few papers have actually included theoretical calculations of non-radial modes, but haven't been able to really match that nicely with the data. So at the moment, we were then left with no clear evidence for non-radial modes in M giants, and no definitive explanation for the structure seen in particular in the Peterson diagram. So what I will be talking about today is a paper that aims exactly at doing that. So by looking at the frequency pattern of non-radial modes in these stars, to see if we can explain what we see in particular in the Peterson diagram, which is a paper that came out, I think, about a month ago. So before I embark on that, I just thought I would put everyone on the same page so we know what kind of stars these are. They are the coolest of the cool giants. They are not only cool, they're really big. And so take the suns, for example. That will at some point evolve and become a K giant, like the ones that Benoit just talked about, and it will look like that. Now let's rescale those two, so we have the sun and the K giant here. When I say an M giant is really big, I mean really, really big. So obviously the structure of this fluffy gentle giant is very different to its smaller cousins, so that we can expect the frequency patterns to be different. The size alone, of course, means that the periods of pulsation are very different. And so take, for example, the sun here, which pulsates with 5-minute periods. We can observe that for only a few days and actually clearly resolve individual modes. We can do the same for a K giant if we observe for a few weeks or months. But for an M giant, we really need to observe for several years. And so this field of pulsations in M giants have been dominated so far by long time series from ground-based photometry. In particular, the Macho and Ogle surveys have played a big role. So when the space revolution came around, initiated by CoRoT, we only got to the K giants. But with Kepler, we could gradually extend that and go further up as the mission progressed. And so this plot here, which is actually an old plot when you're in a revolution, can now be extended with the Kepler data 2 orders of magnitude in luminosity and frequency, if you like. So after about 3 years, it was time to publish the first results on M giants from Kepler data, and I'm showing here results from the 2 first papers. So on the left, we clearly see excess power from the power spectra of red giants that go below 10 microhertz and all the way up, and even frequencies below 1 microhertz. So we are really in M giant territory here, and we can clearly see individual modes. So one of the main plots from The second paper by Benoit and co-workers is this period luminosity diagram, if you like, although this is not exactly luminosity, but it's a proxy for it, which beautifully shows that the overtone ridges that Benoit had worked on for the K-giants can be extrapolated up to the M-giant regime where the black dots are results from ground-based results from Ogle, and the blue ones are the ones from Kepler. And it shows that we now have mode IDs here shown for the radial fundamental and overtones in this region. And that now brings me to the third paper, which is the one I'll be talking about, and I'll start showing you the results of the models. So we calculated adiabatic frequencies for a series of models of a one solar mass star. And we start out with the main sequence and let it evolve through the subgiant phase all the way down, or all the way up, depending on how you see it, to near the tip of the red giant branch. So each model is represented by its frequencies, and they are the radial modes, the dipoles, and the quadrupoles. And for each model, which is basically a horizontal line of frequencies, are plotted at the new max of that model, and the frequencies are plotted divided by the separation in frequency between overtone modes. So you can essentially read this x-axis as the radial order, if you like. So let's have a look at what the frequencies or the frequency pattern looks like as this model evolves. So the region we're interested in is bracketed by these two dashed lines. That's the region where solar-like oscillations are excited the most. So if we zoom in on the top part, we see that for the main sequence, we have this typical picket fence of equally spaced modes, where in the middle between two adjacent radial modes, we have the dipole mode sitting. And that's the typical asymptotic regime. If we go further down to the beginning of the red giant branch, we have a pattern that is actually quite similar. So what I should tell you here is that instead of having just one dipole mode, we have several, because the acoustic dipole mode in the envelope now couples with a number of G modes in the core, so it appears as a little cluster of modes, but the one that has the largest symbol, which has been scaled with 1 over the square root of inertia, meaning that it is a kind of a pseudo-amplitude of the modes, it reveals the location of our acoustic mode in the envelope. And you can see that the position of that relative to the adjacent radial modes is still roughly halfway in between. So if you see it from a distance, you would see the spectrum as this one being quite similar to our main sequence star up here. So this area of evolution has already been discovered, so to speak, and we have seen that our models actually fit the data pretty well. But if we now keep going, and this is the area that we are now pushing our models, so this is new territory, and if we zoom in on that, that's what's shown over here. We can now see that the frequency spectrum looks markedly different in a qualitative sense. And that is mostly because the dipole modes have now moved from being halfway in between, they have moved to the right and now form one part of what looks like triplet structures for every radial order. So the interesting question now comes, how does it compare with the data? So this is the result of the data, which is essentially power spectra of about 200 stars. Each power spectrum is being represented by a grayscale, a very thin slice, horizontal slice, grayscale. It is plotted at the new max of that power spectrum, and the frequency along the power spectrum has been divided by a reference frequency. And so the power spectra have been stacked one above the other according to their new max. So that's what it looks like in this range of new max. So we are around 1 microhertz and below. So it's essentially this range in the models that I just showed. In the background, you can see some vertical lines, and if you're not colorblind, you can see they are black, red, and blue, according to their mode degree. And they are essentially just interpolation of our model grid. And so it's actually quite remarkable if you look at it, how well our models produce those wiggles and curvatures, or if you like, departures from the asymptotic regime, how they are shown in the data. It is actually astonishing, I would say. I was quite astonished when I saw it. So it was almost like a eureka moment. When I saw that, I thought, wow, yes, of course. Because have a look at this. That's the Peterson diagram. We just have to rotate it by 90 degrees, and you get exactly what you expect, that the period ratios of frequencies that are ordered in this way will create triplet structures. So another striking result from this diagram that we noticed straight away was that the dipole modes, which we now know is that guy sitting there, has an enormous power. And that power relative to the radial mode seems to increase as we go to lower frequency or higher luminosity giants. And that is quite surprising, because we know that even more evolved M giants, like the Miras, are purely radial mode pulsators. And so it was expected that these stars would actually slowly turn off their non-radial modes, so to speak. And so we are quite puzzled why it actually seems to be the opposite, that the dipole modes become stronger. And that's still an open question. So if you want to know all the beauty of this diagram, ask the person who made it, who is this handsome young man. If you can't find him, go to his poster number 14, where it's explained how this diagram was made in all its detail. So that leads me to this plot here, which shows a few examples of power spectra. So they are just extracts or slices out of this diagram, which shows you how we go from this more K-giant type spectrum to more and more triple light structures as we go up in luminosity. For the lower plots here, which are the very highly evolved stars, we don't have the frequency resolution of 4 years Kepler data to actually resolve individual modes within a triplet, if you look at on a star-by-star basis. But if you stack them next to each other, you can see that there is power generally to the right, and that width there from the high mode here plus the not so strong modes here is actually the width that corresponds to the width of that triplet. So we can still actually do mode identification if you like. Now the final bit I wanted to talk about is related to what some people might have noticed while I've been speaking. It is that this mode here, the radial fundamental mode, and here the overtones, indicate that there are some modes here at a lower frequency than the fundamental radial mode. And you might then also, because you know the asymptotic relation, or so you can actually say that these non-radial modes here are the fundamental dipole and quadrupole. So what the heck are these? And so we have been puzzling a bit about that, and Jörn came with a good idea because he worked at that during his PhD. Would they be F modes? So the question is these guys here sitting here at a lower frequency than the fundamental radial? When we look through the model grid, they appear all along the red giant branch. And they are kind of being born, if you like, very early on. So let's just have a look at a few spectra with those fat arrows there. So I'll just show them as frequency spectra to give you an idea here. So now I show a pseudo-frequency spectra of my model frequencies. The peak heights of the fundamental and overtone radial modes are just set to 1, and then the peak heights of the quadrupole modes have been normalized using their inertia. And what you can see then is the fundamental mode is the one sitting here, as the G modes, which are these ones at lower frequency, when they start to move up here, they start to mix, and we get these little clusters of modes, which is essentially a resonance. And we can see that this part here, which is kind of a shoulder to that, separates out and becomes this new F mode. Physically, we can accept that for a quadrupole mode, but for a dipole mode, that's a bit harder, because that would move the center of mass. But we see a similar thing going on. We see these bunch of modes separating out, and they seem to couple to something in the envelope that apparently has both an envelope component or surface component and an internal structure that avoids it actually moving the center of mass, because that wouldn't be physical. But that is certainly still a work in progress. We are just waving our hands at the moment. So I would say in summary, M giants are cool and really, really big. But not only that, we have seen that their frequency spectra show triple structures, which now completely explains the patterns that we have seen early on for years and scratching our heads what the heck they were, that they are just that. It's just typical solar-like spectrum taken to the extreme, where we have non-asymptotic behavior. But we also found that the dipole modes are dominating as we go to more luminous stars. Question mark. Why? And we found some puzzling new modes below the fundamental radial mode, and we don't still have a clue really what it is, but we think they might be related to F modes. So you might argue this is one step forward and two steps back. But I would say I think it's quite evident now that the M giants really have shown they are part of the revolution, and I think in the near future we will see more exciting results. Thank you.
Questions? Bjorn?
Thank you. 3 comments on the question, if I may. First comment, of course we can't have an F mode for L equals 1, because that would move the center of mass, but we can have a mode that almost looks like an F mode in the envelope, and then have the core takes care of the center of mass, and I think that is what's going on here. Second comment, we shouldn't be surprised to see triplet structures, maybe, because we don't even understand why we see the normal pattern in red giants. It's not related to the normal asymptotics of main sequence stars, because that doesn't have the core. So the fact that we have the universal pattern, as some calls it, is not because the red giants behave like the main sequence stars. There's some other effects causing that pattern which we don't understand. And so it's no surprise that we don't understand the triplet structure either. It's part of the same story. And then maybe just a question. How do you know that the Miras are radial mode pulsators, not L equals 1 pulsators?
It's a good question. How do I know? I just know from literature, I guess. So I would have to pass that on to the Mira experts.
Having those large radial velocity amplitudes are difficult to explain from non-radial pulsations. I think that's the commonly used argument in the literature.
But if Miras pulsate in the fundamental mode.
Yep.
Yeah. The other thing is interferometry would presumably show an asymmetry if you followed a Mira during its pulsation cycle. Now, I don't know if the data are good enough yet, but that might be something people would like to try.
Could you say a few words of how these modes are excited? This may be relevant to this question about why dipole modes dominate, because if you have an epsilon mechanism involving motion between core and envelope, I would expect dipole mode to be most important.
If we look at the amplitudes of these stars, at least most of the sample that we looked at, they pretty much follow the solar-like patterns. So for many of them, it seems to be solar-like oscillations, like granulation excited. But at some point, obviously, there must be another mechanism kicking in, because we know that happens in the Miras, where the amplitudes are significantly larger. So there is some transition going on at some point. But that's not something we have at all looked at in this paper.
I'm a bit puzzled about the evolution stage of those objects you are mentioning, because I had in mind that the object observed and analyzed by Benoit Mosser with Hoggle data were AGB stars. And then here you present all these objects as an evolution on the RGB toward the tip of the RGB, right?
Yes.
While the other object should be older, first gone to the horizontal branch and then up again. So I'm a bit puzzled by those, what is common between the object you are discussing here and the one discussed with Benoit? How comes that for the one discussed with Benoit, we needed 10 years of Hubble data, and you can do it here with few years, with less years of Kepler? So you see what I mean?
I'm not exactly sure what you're asking. I mean, if you
The
look
object you mentioned and compare with Benoit at a point seems to be, or at least you present them are object on the RGB, just a bit extending the observation by having longer observation, the Kepler observation on the RGB by having the latest time series. That's it?
Yeah, so the time series length between what was in this paper and Benoit's are not that different. So the range in frequency or new maxes that we probe are also quite similar. So there can certainly be stars in this sample that are not on the RGB, but on the AGB, but that they match.
But your models were on the RGB, right?
My models were only for RGB, yes.
Okay.
And we know from the pure luminosity diagram that there is actually a slight shift in the ridges when you compare RGB and AGB. But because the way we compared the models with the data, if one of our stars was an AGB, we would rescale it to match an RGB model, because it wouldn't change the qualitative pattern that we were looking for. We weren't looking for these subtle shifts.
Okay, it's not a question, it's not a remark, it's an invitation. In fact, Denise knows that I disagree with part of the identification, and because you have seen in the diagram that there is the choice of a reference frequency is very important, and any problem related to this reference will translate into biased results. So according to me, there is a problem in part of your identification because scaling relations, we have scaling relation everywhere, have just a discontinuity in your data. So I invite everybody to discuss this problem. It's very interesting to have the opportunity to compare ground-based data and know this 4-year-long data and to see what is clear and what is not yet fully clear.
Do I have time to respond? In one word? In one slide? I anticipated the question. So what you can see here is the distance from 0 to the fundamental mode is significantly larger than the distance between overtone modes. Okay? Our mode identification shows the same. Distance from 0 to the fundamental, what we call N1, is significantly larger than here. Whereas Benoit would say this is N2, and therefore that N1 should sit somewhere here. And then that I would say that doesn't agree with what we see here. So that's the strongest argument. There's another argument, which is that we can see the gradual change in how power shifts. In other way, we can see actually the acoustic cutoff frequency cutting away power here. And if we had to change our mode ID for the lowest ones, which is the one Benoit disagree on, it means pushing these two ridges one order over here, which would make this smooth transition suddenly have a kink. It's a less strong argument, but it certainly supports what I believe is the right mode identification. But it might turn out to be one of those bets of a bottle of champagne that never gets solved. Right, John? Okay, thank you.